I put human sunscreen on a fragile leaf, and the difference is absolute madness. Sunlight is powerful, but yesterday I noticed something strange about my greenhouse tomatoes. The ones near the glass were fine, while the exposed ones looked completely scorched. I grabbed a bottle of everyday sunscreen and wondered, how does this actually work? I decided to test it by painting this simple white lotion onto a fragile leaf. Under a UV camera, the white cream instantly turned pitch black. It's a literal shield. But what exactly is happening at the microscopic level to fight off this solar radiation? To understand, I mapped out the two distinct types of solar energy, UVA and UVB. UVB rays are short and aggressive, rapidly burning the top layer of our skin. But UVA rays? They are incredibly sneaky and penetrate deep into our cellular DNA. I set up a high-powered UV lamp over a fresh tomato to simulate this attack. Without protection, the UV photons violently bombard the delicate cellular structure on the tomato's surface. So, how do we stop it? Well, there are two completely different chemical defense strategies. First, I tested mineral filters, like this jar of pure zinc oxide powder. I carefully mixed it into a thick paste and coated a dark piece of slate. At a microscopic level, these brilliant white minerals act like millions of tiny physical mirrors. When harsh UV light hits the coated slate, the harmful radiation simply scatters and reflects. Have you ever noticed that annoying white cast? That's just harmless visible light bouncing right back. To fix this, scientists grind these minerals into microscopic nanoparticles so visible light passes through. But what about clear chemical sunscreens? I assumed they worked exactly the same physical way. I applied a chemical filter to a piece of thermal paper and hit the bright lights. Instead of reflecting the light away, the coated paper actually started getting surprisingly hot. Here is the massive twist. Chemical sunscreens don't block light at all. They eat it. They act like microscopic sponges, absorbing dangerous UV photons into their own complex molecular structure. Then, they convert that destructive radiation into completely harmless heat energy that safely radiates away. But just like a kitchen sponge, there is a limit to what they can hold. I left the chemical filter under the intense UV lamp for 2 full, uninterrupted hours. The molecules physically degraded, breaking apart until the protective barrier completely collapsed and utterly failed. This rapid molecular breakdown is exactly why you must strictly reapply it every 2 hours. But the active filters are completely useless without the vehicle, the lotion that suspends them evenly. I mixed oil and water to create a thick emulsion, trapping filters inside microscopic suspended droplets. To test adhesion, I rubbed this emulsion onto the porous, textured skin of a fresh lemon. The lotion perfectly filled every microcrevice, ensuring no UV rays could slip through the cracks. However, what happens when this carefully engineered chemistry washes off into our fragile local water systems? I gently rinsed the coated lemon in a glass bowl, watching the complex chemicals dissolve. Certain chemical filters can actually disrupt the delicate biology of aquatic ecosystems and vulnerable coral reefs. That's why I always prefer using a reef-safe mineral option when working near the farm's water. I dabbed a little on my nose. It is a simple chemical marvel protecting us daily. Whether bouncing rays or absorbing them, sunscreen is a brilliant microscopic bodyguard for your vulnerable cells. My greenhouse tomatoes are perfectly safe, and so is the skin hidden under my fur. What everyday chemical or hidden system should we investigate next here on the century-old farm?